Hey folks, so I'll be going over the HRM paper today. I think it carries a lot of significance and one that is surprisingly easy to understand. So the paper's core claim is that current reasoning LLMs have, such as ChatGPT's O series of models, have several limitations to them. So the first is that language is not a substrate for thought, meaning humans don't use language to think. That is, we reason in a much more abstract way. One of the best examples of this is to simply trace back our genetic ancestors, and then we will eventually reach a point where language had not yet evolved, yet beings still demonstrated intelligence and situational understanding. So I guess it would be fair to say that we can decouple language from intelligence. Maybe you could still make a case that intelligence eventually leads to language use, but I do not know if it would be accurate to frame it the other way around. So, even within our own animal kingdom, we can see examples of species that do not have fully developed vocal cords, but they still demonstrate intelligence. And the second disadvantage with the current reasoning LLMs is that the chain of thought reasoning essentially relies on having a very large context window, where a section of this context window is dedicated to reasoning tokens that remain hidden unless you click on the expand button. So, with the release of ChatGPT 5, this would be that thinking animation that you see. So when you click on it, it kind of summarizes your reasoning tokens. So this is more of a UI play than it is an engineering marvel. And these reasoning tokens, they remain frozen in the message array. So one bad decision can kind of derail the entire resulting future chain of thought. So the authors take these things into account and they propose a new architecture, and they obviously name it the HRM. And the HRM that they use in this paper, it only consists of 27 million parameters, and they show that it outperforms models like DeepSeek R1 and ChatGPT's O3 Mini High on the Arc AGI1 dataset, right under their specific setup, which I will describe later. But otherwise, I think this is a really cool paper, and it is important that we know about it. Okay, so in this section, the authors start by saying that even though deep learning is an evolution of classical ML and relies on increasing the representational power by stacking layers, modern LLMs are actually still quite shallow. So the multi-billion parameter models that we are seeing are more so wide than they are deep. And in the paper, they also say that for specifically for the Sudoku test, adding layers to the non-HRM model does increase in accuracy, but it is still far from optimal with even very deep networks. Let's jump over and take a look at a graph. Okay, so the images that I'll be showing are taken directly from the paper, from the HRM paper. The only reason I've isolated them is because it's much more convenient for me to explain it this way. Okay, so in this graph, we see that x represents the number of parameters and y is the accuracy. There are two curves. The dark blue line fixes width and adds parameters by increasing the depth, while the gray line fixes the depth at 8 and adds parameters by increasing the width. We see that for the same parameter budget, increasing depth helps much more than increasing width, although at some point it eventually leads to diminishing returns. So we're starting to formulate what the authors want to fix. And in the further section, they compare chain of thought reasoning to biological reasoning. To be more specific, they don't really actually criticize chain of thought itself, but rather how it's executed. They say that in the human brain also executes very long chains of thought, but it does so in a latent space without any constant translation back to language at each step, which the current LLM reasoning models do. Okay, so the solution then must be to just let the LLMs reason latently, right? The authors say that the fixed depth of LLMs is a limiting factor that does not allow for latent reasoning. When I first heard this, I was confused because, what does it mean? What do you mean by LLMs are fixed depth? I thought that LLMs are infinitely deep, right? Because in theory, you can generate a billion word passage or even a trillion word passage for that matter. But what I did was confuse infinite time with infinite depth. Because autoregressive models like LLMs that take previous token as the input and generate the next token can in theory run infinitely. But depth is measured not as a function of the number of tokens generated, but rather as a number of layers it passes through for the generation of one single token, which in the case of transformers is fixed, and which is what the paper also indicates. Okay, so then the solution must be to simply make the LLMs infinitely deep, right? Seems simple enough. Obviously not quite. And let's take a look at another graph to understand this a little better. So in this graph, the x represents the time steps and then y represents the forward residuals. Let me quickly explain what forward residuals mean. Think of a model running for n time steps. So at each time step, its internal state gets updated by some value delta x. Okay. So if this, for whatever reason, this delta x becomes very small or insignificant, the hidden state stops changing much, and the additional steps are unlikely to add anything useful, and you're just mostly burning compute, which is what we see here from 40 to 60, where the forward residuals are almost zero. So there is no point of propagating any further. Adding more layers or making it infinitely deep doesn't really help further than that point. To kind of solidify this example, let's kind of, maybe I'll explain it in using a slightly different example. Let's assume that we're reading a 100-page book, right? With each page, our internal mental state is updated by some value delta x. Now, this delta x can be thought of new information that is being added to our brain with every page that we are reading. In the book, let's assume that only the first 20 pages are new and original content, and the next 80 pages is just some combination of the first 20 pages. So while you may still keep reading after the first 20 pages, your mental state isn't really changing, if at all. It's just mostly a waste of your time and compute. So while you may provide it infinitely deep networks, it would be the same as reading a book with an infinite number of pages, but after page number 20, you're not really gaining anything new. So you're just burning compute. Okay, so the authors want deep models with dynamic depth while still being able to learn new things. And this is where they propose the hierarchical reasoning model. So, this is where the authors propose the hierarchical reasoning model. It's essentially made up of four blocks: the input block, the L block, the H block, and the output block. Although we are only interested in the L and H block. The L and H block correspond to two levels of the brain: one which is for slow, high level thinking, and the other is for fast, detailed, low level thinking. Now, I have not independently read or have any experience in biology or neuroscience, so I'm definitely not going to get all the details right. But the way I like to imagine it is that the motor skills are managed by the L block, which is fast, responsive, and also happens without any effort, as though on autopilot. And then you have the slower part, which kind of kicks in when you're trying to understand a really complex math formula, perhaps. So these are the L and H blocks. Now, from the last section, as a refresher, we know that we need a model capable of variable depth in order to support latent reasoning. However, variable as well as deep networks come with their own set of problems. One of the main issues with recurrent networks, as we have read in the last section, is that they converge way too quick and do not utilize the added depth, even if it is present. So we need a model that has variable depth and also one that does not converge very early. And for that, let's take a look at how the HRM works. So I drew a few diagrams on draw.io to kind of explain a few details. Let's only concentrate on the L and H block, which are of importance. Remember that there is only one H block and then there is only one L block. Each block has its own internal state, kind of similar to how we have our own internal state in the brain. For the H block, let's call it ZH, and for the L block, let's call it ZL. And then we also have the input X. Now, in the next diagram, it might seem very confusing, but just note that it is exactly the same H and L block, but being repeated over several time steps. There is nothing more to it. Okay, so just by the means of visual analysis, you will see that the L block here takes in three values as input. The input X, which remains constant, and then the previous time step H block's internal state, and then you also have the internal state of the L block from the previous time step. It takes these three values and it kind of recomputes its internal state, which is then passed on to the L block for the next time step. So this process keeps happening until the L block reaches convergence or equilibrium or a fixed point. Can be used interchangeably, but essentially it's the point where if you supply the input, you will get back the same as the output. So the input no longer changes the output. It's just at fixed state. So when you reach this point, what you do is then you update the H block. Now again, through visual analysis, you will see that the H block kind of takes in two inputs. First is the current L block at time step t, its internal state, and then you also have the internal state from the H block at the previous time step. It takes these two values in, and then it recomputes its own internal state, which is then passed on to the L block in the next for the next set of runs. Now, one question that you might have is, why do we have to rerun the L block, right? Why do we have to rerun the L blocks again? Because isn't it counterintuitive to everything that we have learned? We have learned that, once we reach convergence, which the paper says that the L block does reach convergence at time step t. So when we reach convergence, we are not really, gaining anything if we, even though we run the model for further time steps. So why do we do that now? Well, you would be correct, and if the same inputs were being supplied to the model, that is, if the internal state from this block, the input were being supplied, then the L block would continue to remain in convergence. But note that we have now updated the H block, and the internal state is now a new value. So a new value was then supplied to the L block as input, which kind of resets its internal state so that it gains a very high residual, and then it has now the opportunity to propagate further and learn new things. Let's just take a look at the a graphical example, and then you will see that we start off with the L block here, and then as the time proceeds, the L block kind of reaches a point. Well, I have to first say that I think I told you that the L block is run until it reaches equilibrium or fixed state, right? But in practice, however, we just run the L block t number of times. Okay, so at the L block, now that it is run for t times, you will see that it's reached a point where the residuals is very low. At which point, what happens is the H block is updated, and then the new value is given to the L block, which kind of resets its forward residual to a very high value, and then it proceeds for t time steps, and then the H block is updated, and then again it resets its residual, and then it kind of propagates further. So this process keeps happening, and then you will see that the H block also converges towards the end, but it does so in a very smooth and slow manner, giving it enough opportunity for the model to pick up new things and learn and make better predictions. And then you can kind of directly contrast it with the recurrent neural network, which has only one block, and then you will see that it kind of just crashes down to zero very quickly. So there is no real opportunity for it to kind of go beyond a certain point, whereas with the HRM there is. Okay, so to kind of, what do you say, solidify this example that we just we the graph that we just described, I think it would be nice to just imagine a scenario, right? Let's say that the H block is a professor, and then the L block is a student working under the professor's mentorship, right? So they're both trying to accomplish a common goal. The student, or the L block, works in quick intervals using its existing knowledge, right? But after some time, reaches a point where no further progress can be made. At which point, what happens is the professor block looks at the work that was done, update its own knowledge, which is the H block update, and then suggests a new approach for the student to take, right, which is the L block, thus allowing for a replenished learning cycle. So this process continues for a total of n cross t times, and only at the end of nt steps is the output extracted. So obviously we are letting it run for a really really long time, and during this time the residuals don't fall flat to zero. So I'd like to make a note, because we run this through a several time steps, right? Optimization becomes a problem since we're dealing with the O of NT memory. If you backpropagate through all of the NT steps, to handle this, the paper does propose a technique, right, where you approximate the optimization step, so you can use a fixed O of one memory and avoid unrolling through time for the backward pass. If you want more details, I'm gonna add a video to the playlist. But even if you do not watch it, I don't think that's going to be a problem because it doesn't take away from the paper's main ideas. So you're totally fine even if you don't. But if you really want to convince yourself why the one-step approximation works, I would suggest that you do watch that video. Okay, so then the authors also talk about this technique called deep supervision. We do know that, from what we've been speaking about and reading through, that each example is propagated a total of NT times with with deep supervision, right? So essentially, now they rerun the same example input m times. So in total, the example is propagated through mnt steps, and each repetition is called as a segment, right? And then there are, of course, a total of m segments per cycle. And at the end of each segment, an optimization cycle is run, and then the internal states of the last HNL blocks are detached from the gradient graph and passed as input to the next segment. Uh, it's like it's almost like writing a five paragraph essay, but where the teacher gives you quick grades after each paragraph instead of just only grading at the very end. Um, yeah, let's check this out. So, you repeat this a total number of t steps, and then this whole process gets kind of repeated over nt time steps, right? Now, with deep supervision, you will repeat this NT time steps a total of M times, where at the end of each segment you run an optimization cycle. Okay, so now we move to the paper's most interesting sections. And think about it. Let's assume that you're given two tasks. One is to either pick between a black or a gray shirt, and the other is to buy or rent a home. Now, both in essence are binary choices, right? But then, which would you spend more time thinking about? Well, you may spend a few minutes, an hour, or maybe an entire day trying to decide which shirt to pick. But the decision to either buy or rent a home usually spans several weeks, months, or maybe even years in some cases. So clearly, one requires more brain compute than the other. And I guess even generally speaking, there is a correlation between task difficulty and the amount of time you take to arrive at a decision. So what about the alternative where, regardless of the difficulty, we were all forced to spend only 10 minutes on every problem in life? That would be terrible. And similarly, uh, we need to allow the model to have autonomy over how much time it spends on any given task. Well, in the last section, we spoke about deep supervision, where the same input is run through m different segments, right? So we need to allow the model to have the choice of picking what this m is. And the paper kind of proposes the same, and it calls it adaptive computational time. And it kind of uses a Q learning policy to achieve this, which I think is extremely cool. So now, in addition to the input block, the L and H block, and the output block, we now have a final addition to the HRM architecture, which is a Q block. Uh, so, at the end of each segment, right, the end of each segment M, the Q block looks at the H block's final internal state and decides between two actions, whether to continue thinking even further, which would mean that we would add another segment, or to stop execution and return the output in its current state. So, of course, the actions that the Q block can pick from are either Q halt or Q continue, right? So, a few more details about this. So, the maximum number of segments, which is M max, that it can think for, is chosen based on can be chosen based on the compute available. Uh, and also, we pick a number M minimum, right, to force a minimum number of thinking segments. I guess going back to our student and professor example, the Q block would be the organization that is funding the professor or the entire research. So, and at the end of each segment, the Q block, which is a funding organization, will talk to the H block, which is a professor in our example, and checks if the current research output is sufficient. If yes, the work is then marked complete and it is evaluated. If no, then the HNL block, which is a professor and the student in our example, runs for another segment, and the end of that segment, the work is again re-evaluated in the same way by the Q block. Now, funnily enough, M max in our example would represent the maximum allocated funds, because after that it doesn't really matter what the Q block thinks because they're out of funds, and the work will be returned for evaluation no matter what. We can fold the Q block into the training loop of our HRM, right? So the expectation really is that the Q block learns to pick how long to think for based on the task difficulty. Think about it. It's really cool that it can even do that. Um, and that's it really. These are the main ideas in the paper. In the future, I may add another video to the playlist where we go through the results section. Let me know if you find that to be of interest. But even if I do not, you're fully equipped to understand it yourself just by going through the paper now that you have a picture of what the main ideas are. And I just think it's extremely cool how the dynamic outer loop handled by the Q block works. Of course, there are a lot of open questions that the paper kind of leaves you with. But given its compute requirements, maybe we can train our own models and answer our own questions, right? Because it's quite easy to train the model from scratch, even on a relatively easy to acquire GPU like a 4090. Uh, I guess relatively is doing a lot of heavy lifting here, but it is certainly doable if we choose to. And I think there is a lot of merit in trying to run the trying to run this model locally to see if we can maybe modify it a little bit and kind of fit it to our own needs.